So Krishna, we've let everyone who's here in.
Okay. Good afternoon, everybody. I'm Krishna Kalluri, alternate counselor of SCALACS, that is the Southern California local section of the American Chemical Society. And I thank Veronica Emilio, our chair of SCALACS, for overseeing the event. This seminar is facilitated by an innovative projects grant, IPG grant from the local section activities committee of the ACS. And we are conducting this in collaboration with the Georgia local section of the ACS, as well as the senior chemist committee of the national ACS. Since the topic is on bioelectronics, I would briefly explain what this term means for the sake of those in the audience, especially the students who are not familiar with it. Bioelectronics is a multidisciplinary field that merges biology and electronics to create devices and systems that monitor, interact with, or control biological processes. From the chemistry side, it involves material chemistry, biomolecule immobilization, and electrochemical biosensing. In recent years, commercial wearable bioelectronics are incorporated into clothing and smart watches, rendering them the ability to monitor body temperature, pulse rate, and even analyze heart waveforms. Flexible bioelectronics, including wearable and implantable electronics, have revolutionized the way humans interact with machines due to the fact that they can provide natural and seamless interactions with humans and keep stable and durable at strained states. As sensor elements are biomimetic actuators, flexible bioelectronics can dynamically sense and monitor physiological signals, reveal real-time physical health information, and provide timely, precise stimulation or treatments. Thus, the flexible bioelectronics are playing increasingly important roles in human health monitoring and disease treatment, which will significantly change the future of healthcare as well as our relationships with electronics. Enough of my introduction, so I will pass on to our colleague, Professor Jessica Lu of Biola University, to introduce the speaker, and then we can carry on. Jessica?
Great. Thank you. Thank you very much, Krishna. I have the privilege of introducing Dr. Chen. So Dr. Jun Chen is an associate professor with tenure in the Department of Bioengineering at the University of California, Los Angeles. His research focuses on soft matter innovation for healthcare and energy. He has published 2 books and 380 journal articles, with 280 of them as the corresponding author. His publications were cited 57,420 times in literature. For example, his article titled Progress in Triboelectric Nanogenerators as a New Energy Technology and Self-Powered Sensors, published in 2015 in the journal Energy and Environmental Science, was cited in 2,158 publications. The article on wearable pressure sensors for pressure wave monitoring, published in 2022 in the journal Advanced Materials, was cited in 761 literature publications. The article Eardrum-Inspired Active Sensors for Self-Powered Cardiovascular System Characterization and Throat-Attached Anti-Interference Voice Recognition, published in Advanced Materials, was referenced by 609 articles, demonstrating his multidisciplinary strengths and the significance of his research on materials for biological applications. He also filed 18 US patents with 1 licensed. With a current H-index of 128, Dr. Chen was identified to be one of the world's most influential researchers in the field of materials science on the Web of Science. Among his many awards are the V.M. Watanabe Excellence in Research Award, awarded to one faculty per year at the UCLA Samueli School of Engineering, the ACS Nano Lectureship, the Materials Research Society Outstanding Early Career Investigator Award, the Hisako Terasaki Young Innovator Award, the Stephanie L. Kwolek Prize, the Shu Chen Early Career Award, the Asian American Academy of Science and Engineering Rising Star Award, the American Society of Mechanical Engineers Rising Star of Mechanical Engineering, the Biomolecular Engineering and Cellular and Molecular Bioengineering Society Rising Star Award, the UCLA Faculty Mentor Award, UCLA Society of Hellman Fellows Award, Georgia Tech Alumni 40 Under 40, Office of Naval Research Young Investigator Award, American Heart Association Innovative Project Award, Transformational Project Award, as well as Second Century Early Faculty Independence Award. The National Institutes of Health, UCLA CTSI KL2 Translational Science Award, and the Brain and Behavior Research Young Investigator Award, Okawa Foundation Research Award, Advanced Materials Rising Star Award, Materials Today Rising Star Award, Chemical Society Review Emerging Investigator Award, Nano Research Young Innovator Award, the ACS Polymeric Materials Science and Engineering Division Young Investigator Award, the Clarivate Highly Cited Researchers Designation for 2019 through 2024, among others. And beyond his research activities, Dr. Chen serves as the Executive Editor-in-Chief of MEDX and an Associate Editor for Biosensors and Bioelectronics, Materials Research Society Communications, among others. The title of Dr. Chen's talk is Discovering Magnetoelasticity in Soft Matter for Bioelectronics. I now hand over this time to Dr. Chen.
Okay, thank you very much for Jessica for the very detailed introduction. Yeah, I highly appreciate that. And yeah, so it's really nice to meet everyone here. So I'm Chen from UCLA Bioengineering, and today I would like to share a story entitled Discovering Magnetoelasticity Soft Matter for Bioelectronics. So before my presentation, I would like to give you a brief introduction why bioelectronics research is very important. So look at here, this diagram to show the relationship between the disease burden and the cost. So our current healthcare system is based on the typical current intervention. So what does it mean? For example, if this morning we wake up, you have a headache, you feel discomfort, then you will contact doctor. So doctor will check his schedules and, oh, Dr. Chen, maybe earliest available time is tomorrow afternoon. Then I have to wait till tomorrow afternoon. I drive a car to clinic center. So the doctor will give me 10 to 20 minutes treatment and then ask me to pick up some medicine in the CVS and then ask me to check back again, maybe 1 week later. So you can see this is the current healthcare system in the United States. It's based on the disease management, and it certainly has a high cost, low efficiency. High cost most mean, oh, I have a headache, then probably I cannot go to office to work today. I have to stay in home and drag a long distance to a clinic center, especially LA has a very heavy traffic jam. And also, also you have to take some medicine to bring back your to a healthy state. And the low efficiency most mean the low doctor-patient efficiency. So you wait for 1 day and then drive a long distance to a clinic center. They just give you 10 to 20 minute treatment or diagnosis. So you can see this very low doctor-patient efficiency. So as the rapid advancement of Internet of Things or 5G or 6G wireless network will be think about, can we do early molecular detection? So what does it mean? For example, if I have a body temperature sensor, it keeps reporting my body temperature. And this morning when I wake up, a body temperature sensor tell me that actually your body temperature is abnormally high compared with your body temperature historical data stored in the cloud. So that means you have potential to get a headache. You can share this data with the doctor over distance by use email, by use iMessage, or many other channels. So then the doctor will give you immediate suggestions. So Dr. Chen, maybe you're working so hard and it's time for you to take good rest and drink some hot water and don't go to office in the morning. And then when you, after your body temperature back to normal range, then you can continue to work very hard. So you can see that is so-called the health call based on Earth's molecular detection, and also is so-called personalized health call. You can see this new module actually based on the disease prevention rather than disease management, and also is focused on health enhancement. It has high quality and low cost. High quality most mean we don't need to go soften the bad feeling like a headache of this kind of bad feeling. Low cost that we don't need to completely stop working. We just take longer sleep, drink more hot water. So that is what will come to us. So this is so-called personal health call. You can see to realize this type of health call transformation, the bioelectronic device like the body temperature sensor I mentioned just now plays very important role here. They are able to change the current reactive disease-centric health call system to a personalized module focused on disease promotion and health and disease prevention, health promotion. So you can see definitely bioelectronics research very important. It can promote or facilitate our current health call transformation. So when we look at the bioelectronic devices, so no matter it's wearable bioelectronic devices or implantable bioelectronic devices, for wearable devices, we have a lot of sweat on the skin. So for implantable devices in the human body, actually, we have a lot of biofluid. So overall, the working environment of bioelectronic devices actually is a high humidity environment. But for most of the current bioelectronic devices, they are not waterproof. So if you wanted to make a device waterproof, you have to add additional encapsulation layer on the device and then to enhance the waterproofness of the devices. So after I joined the UCLA, I have a bit think about, can I develop intrinsic waterproof bioelectronic devices? So probably we don't need to use the encapsulation layer to make a device waterproof, because if the device is inherently waterproof from fundamental working principles, probably this problem will be solved in a very better way, because those encapsulation layer usually will make a device very bulky, reduce the sensitivity, or compromise other performance. So how to develop inherently or intrinsic waterproof devices? So after I think about the device, this problem, so how can I find a solution for that? So I usually, when I find a product problem around us, if I wanted to find a solution for them, I usually wanted to start from a very fundamental science. So for example, when I look at for this problem, so I have a look at the fundamental energy nature. So the matter is optical energy, electric energy, thermal energy, or some other energy format. Most of them actually very easily electrically impacted by water, by the humidity. But magnetic field is able to penetrate water. So probably if I get some power from the magnetic energy or magnetic field, probably we are able to build up some intrinsic waterproof bioelectronic devices. So let's come to the keywords of today's speech. That is magnetoelasticity. So what is magnetoelasticity or magnetoelastic effect? So actually this is a very traditional phenomenon, actually, or it's not new. So actually magnetoelastic effect is discovered by Emilio Villari in 1865. He is an Italian scientist. He found that when you apply mechanical pressure to some rigid metal alloy, like the Teflon-D I show here, when you apply mechanical pressure up to 30 megapascal, you can see a decreased magnetic flux density. So when you reduce the pressure, so magnetic flux density back to original state. So you can see this change is totally reversible. That's because when you apply mechanical pressure to this rigid metal alloy, the pressure will induce magnetic dipole tilted in those magnetic domain in those rigid metal alloy. With a result, in the bulky materials, we can observe a decreased magnetic flux density. So this effect can only observe the rigid metal alloy like Teflon-D or Gaffron I show here. So the required mechanical pressure up to 30 megapascal. So in the past 150 years, so those effects can only apply for building environment control, because at those application scenarios, they're able to provide mechanical pressure up to 30 megapascal. So last until 2021, our group at UCLA, we just mix some magnetoelastic particles with soft polymers. We found in this soft composite, we can also observe a magnetic flow density change under pressure. But the required mechanical pressure is reduced from previously 30 megapascal to about 100 kilopascal. You can see with those tiny mechanical pressure, you can see in this soft composite, you can still observe decreased magnetic flow density. We reduce first the magnetic flow density back to original state. So to understand what's going on in these soft composite materials, we do some theoretical understanding first. So you can see that actually we found out those magnetic particles are form a waving chain shape in the polymer matrix. So those waving chain shape will also give us a microscopic magnetization domains. Look at here. So we apply mechanical pressure in some microscopic magnetization domains that also induce magnetic field, magnetic dipole tilted. With the result, they can observe reduce the magnetic flow density. While showing that actually this wavy chain model is able to explain this serial magnetoelastic effect in soft system or for those systems with arbitrary geometry or with a system with a surface deformation or with arbitrary deformation modules to this soft composite system and also arbitrary magnetization profiles. So basically you can see actually this wavy chain model is a good explanation of those general magnetoelastic effect across different soft systems to give us very theoretical understanding about this phenomena. So beyond our theoretical effort, we also wanted to harness this phenomena to show some real practical societal impact. So with that, we developed a fundamental new platform technology we named magnetoelastic generator. So how to do that? So we just take a soft composite as a magnetochemical coupling layer, MC layer for short. So that soft composite, that we apply mechanical pressure to this MC layer. So magnetic pressure, the mechanical force will induce magnetic field variation to induce mechanical to magnetic conversion. So on the top of our magnetic MC layer, we pattern some soft conductor coil to form this magnetic induction layer, MI layer for short. So those MI layer is able to pick up magnetic field variation to generate useful current in the internal circuitry. So we call it magnetoelastic generator. So because this is all-in-one body design and also magnetic field is able to penetrate water, so to make this platform technology basically intrinsic waterproof, that's actually give a solution to my previous pursuit about developing intrinsic waterproof bioelectronic devices. So basically, with this fundamental new platform technology, we build up different soft magnetoelastic bioelectronics for biomonitoring, for therapeutics, and energy applications. For biomonitoring here or sensing here, we mostly because those platform is able to convert tiny biomechanical pressure like eyeball movement, respiration, pulsar wave, those kind of vibration, this kind of mechanical pressure into high fidelity electric signal. Because those electric signal contains information about the biomechanical motions, so we can use them to monitor respiration rate, monitor the heart rate, but also monitoring your pulsar velocity, blood pressure, many other parameters. For therapy here, mostly because those general electricity is able to promote, for example, bone healing, bone regeneration, some other applications provide other therapeutic applications. For energy, because it's magnetoelastic bioelectronics I mentioned now, is able to convert mechanical pressure into electricity. So basically, those devices actually is a power supplier is able to provide electricity to wearable devices or implantable devices for energy applications. So here I just wanted to showcase some real application scenarios to show you how can we harness this fundamental new platform technology to build up some intrinsic waterproof bioelectronics for sensing. So here you can see that we're able to make the devices in a one-dimensional magnetoelastic microfibers. So when we weave these fibers with conductive yarns, we can form this kind of magnetoelastic text sensors. So you can see when the wire this text sensor against western artery, this kind of west artery side. So this kind of tiny mechanical pressure from bottom vessel this kind of compression, expansion, this could be detected by the sensors that generate useful current in internal circuitry. So you can see no matter under water situation or with perspiration, in one cardiac cycle, so you can basically that generate very high voltage electric signals. So basically those possible profiles could be continuous monitoring and read out. So by analyzing those generated possible profiles, we can get a lot of cardiovascular this kind of biomechanical informations like the K value, augmentation index, pulse velocity, blood pressure, heart rate, or many other parameters as a continuous this kind of possible monitoring devices. So certainly we're able to use these devices convert eyeball movement into electricity as well as a fatigue diagnostic intervention devices. So you can see this devices is intrinsically waterproof, is able to make a thing as like food wrap. So when they attach the device to the eyelid, so they're able to convert the eyeball movement like a normal blink, fast blink, up and down movement, is eyeball movement induce mechanical pressure into high voltage electric signals. We just analyze those generated electric signal, especially the amplitude information and also frequency information, can calculate the blink eye, this kind of blink duration, close eye duration, and open eye durations. So you can see that actually by analyzing those parameters, we're able to quantify or decoding the fatigue level. So for example, if you drive a car in the highway 405 highway, if you feel sleepy, so actually those generate electricity can also as an electric stimulation to stimulate the eyeball as a refreshment and actually to remind you actually you already get fatigued, and those electric stimulation can refresh your mind and actually form this kind of closed loop fatigue intervention devices. So we can also use them to monitor respiration as well. So the working principle of such device is very easy. We just make the device into a piece of textiles. So this device is able to attach to the belly part of a participant. So during the respiration, your belly is up and down. So this kind of mechanical pressure is able to generate electricity. Look at here, when you do a normal breath, rapid breath, and then coughin. So you can see the generate electricity has different frequency and amplitude information and different patterns. So with this, we can analyze those electric signals, usually with machine learning algorithm. We are able to detect your different respiration behavior, like a normal breath, rapid breath, and coughin, as this kind of continuous respiration monitoring devices. So we can also use this platform technology build up wearable human machine interface devices. You can see this magnetoelastic generator control panel. So you can see that actually even with heavy perspiration and water on your hand, so this actually MEG control panel is able to be responsive to your touching force. So when we generate touch this control panel, so the generate electricity could as a command signal to control this kind of music player. This actually is a music player. So this generate electricity signal can wirelessly control the music player to play the song, pause the song, play next song, and play last song as actually wearable human machine interface devices. Because with all-in-one body design, this device is not only intrinsically waterproof, and also the foldable, rollable to reduce the volume and for easy of transportation in the future. So because this platform technology intrinsically waterproof, so we can also use them for underwater haptic sensing devices as well. So why I wanted to do this type of research? Because actually the Earth's surface covered, 70% of them are covered by water. So in the future, if the resource on land is used up, probably we have to explore resources in the ocean as well. But in the deep ocean, if there's no light, actually it's very hard for you to recognize the items. So here we're developing this magnetoelastic artificial skins for underwater haptic sensors. So you can see actually this artificial skin is able to detect normal force and shear force simultaneously. So you can see that actually you can see this normal force and shear force could detect by this artificial skin. So by this kind of while this artificial skin to touch some items with generate different electric patterns, we're able to recognize small items like this kind of plastic bottoms, paper cup. Actually, this is a very typical ocean waste. So by touching, we're able to recognize those items actually with recognition accuracy about to 95%. So we can also use this platform technology to build up a magnetoelastic keyboard for Parkinson's disease diagnosis. So Parkinson's disease actually is a neuron degenerative diseases. Actually, is a very popular. It's very common, not popular. It's very common among the older group. So when the people get old, actually, they usually have, if they have Parkinson's disease, they have a lot of hand tremor, which is uncontrollable. Actually, here we can use this keyboard to do this kind of early stage screening of Parkinson's diseases. So the working principle of the device is very simple because this intelligent keyboard actually is pressure sensitive. So when the older people typing on the keyboard actually in the most customized ways, because this kind of hand tremor will change as typing behaviors. With that, actually, we can monitor this kind of typing behavior change to indicate whether he has Parkinson's disease or not. So you can see we take the keyboard to the hospital and validate the Parkinson's disease patient. So you can see that when the people typing on this keyboard, actually the flight time, hold time, and applied pressure during typing could be measured. So by analyzing those profiles, we're able to quantify actually how serious the Parkinson's disease is, or do you have potential to get Parkinson's disease? So basically, we developing this as a very accessible, no cost, and you can use them at home setting for early stage as Parkinson's disease screening. So we can also take a further step, use this magnetoelastic device to build up a gel pen. So this gel pen is also pressure sensitive. So when you hold this pen to writing on the papers, because due to hand tremor, Parkinson's disease induced hand tremor will change your writing patterns. So we also validate this pen in a hospital, UCLA hospital. You can see with the people to writing on a piece of paper to write some patterns. So because this hand tremor will change the writing behaviors, you can see they'll induce a lot of irregular, this kind of peaks in the generated electric signals. So basically by analyzing generate this kind of peaks on this pattern, this writing patterns, were able to also to quantify the Parkinson's disease as well. So basically, this is a magnetoelastic gel pen, also could be utilized for Parkinson's disease diagnostics. So these devices this platform technology can not only utilize for this kind of portable, wearable monitoring devices, we can also extend them for implantable bioelectronics as well. So because this device is intrinsically waterproof, here we just build up two-dimensional membrane devices. So when they attach this membrane to the open heart rate, you can see the heart expansion or compression during the heart beating can generate electric signal in the internal circuit. You can see during the diastole or systole, you can see the generate different electric signals. Basically, those electric signals have very high quality, contains our information about the heart beating. So basically, we can use them as implantable cardiovascular monitoring devices. So this two-dimensional magnetoelastic membrane is quite bulky. So very recently, we also can use to reduce further miniaturize the device to build up this kind of human dynamics-driven magnetoelastic vascular graft. So basically, you can say this graft is not a normal graft. Actually, it's a pressure-sensitive graft. So you can say they have very good scalability. We can fabricate them with different diameter, like 1 millimeter, 2 millimeter, 4 millimeter, 5 millimeters. So this device you can see to the bendable and actually it could use a scalable fabrication. So I show you that when we put this vascular graft, we validate the device in a pig model. You can see that actually during the patency, it generates very regular electric signal. If the stenosis happening in this vascular graft, you can see the output signal, both the amplitude and frequency will be largely changed. By doing that, we're able to monitor stenosis in the vascular graft, actually. And this device also can utilize to monitor the heart rate as well. And we're showing that this graph could be implantable to wider range of arteries in the human body. You can see the implant actually when you implant the sensors as deep as about actually 1 centimeters, they can also have some very useful, effective, this kind of electric signal monitoring or measured from these devices. Actually, then we are able to use them for this kind of actually as a smart vascular graph. So there's some for diagnostic of systems. So we can also use them for therapeutic applications as well. So the very first application scenario I want to show you how can we use them for therapeutic applications that do the cell reprogramming. So we're showing that we can use magneto generate electricity to continue to stimulate human fibroblast blood cells after about 14 days stimulation that are able to convert fibroblast blood cells to this kind of neuron cells. So we're showing that actually this have very good effect to convert this kind of new fibroblast cells to neuron cells. So this is so far in the lab is the in vitro study. In the future, probably we can use them to provide some therapeutic to neuron degenerative disease. For example, if you have Parkinson's disease, so we can implant, we can deliver some of yourself have fibroblast cells to this and to some places, and then we can use electric stimulation to convert them into neuron cells. Probably we can provide some therapeutics to the neuron degenerative diseases. So certainly we can use them as assistive therapy devices. Here, for example, we can use them to put up speaking without vocal fold devices. So for example, when you can help me, that's because my vocal folds keep vibrating a general mechanical wave. When this mechanical wave reach your ears, then you can hear my voice. But what if you have dysfunctional vocal fold, but you still wanted to talk? So here, this is a device is able to provide some therapeutic to this diseases or this problem. So here you can see this is a magnetoelastic based wearable sensing and actuation system. It has two components. One is a magnetoelastic sensing component. So this sensing can be able to convert the muscle, this kind of soft muscle vibration into electricity because you have dysfunctional vocal. You have to then but if you still want to talk, so we can use magnetoelastic sensing component to convert the muscle vibration into high voltage electric signal. So you can use general electric signal after processing. We can input into another magnetoelastic actuation layers to induce a membrane vibration. So in a lab, we can speak very short sentence with a muscle vibration like the "Hi Rachel, how are you doing today?" or "Hope experiment going well." Those short sentence. So as assistive therapy to help you speaking with our vocal fold. So we can also use them to provide some personalized muscle phase therapy as well. So this device is this is actually magnetoelastic textile patch, which is very sensitive to tiny pressure, induce a muscle compression or expansion, this muscle stretching behaviors. So when we attach the device onto the arm, so if you have a injury in the gym during the rehab procedure, you have to slowly and gradually exercise the muscle to promote rehab. So here you can see that after you attach this magnetoelastic patch to your muscle, they're able to quantify your muscle behavior, like if you have a leg exercise, excessive exercise, or deficient exercise, because they generate different electric signal with different patterns. Then we can provide precise this kind of control or process this kind of rehab procedures and to promote rehab procedure to promote your rehab process. So as a personalized muscle physiotherapy. So there's some applications for therapeutics. And then lastly is energy. Energy actually, because this device is able to convert mechanical pressure into electricity. So basically, when we integrate those devices into human our clothes during a daily movement, for example, when you wear this text magnetoelastic generator on your arm, when you bend the arms, they're able to convert mechanical pressure into electricity. We can use general electricity to charge some supercapacitors like here you can see. Then we can use them to drive some thermal, this kind of thermometer to monitor body temperature. So similarly, here we can use general electricity to drive electrons watch. So we can also use the general electricity go through fiber resistors to provoke Joule heating. So then this can increase your temperature of clothes. So in the cold winter, for example, in the Boston areas. So if you walk outside, these textiles are able to convert biomechanical pressure into electricity. So those general electricity can increase the temperature of your clothes. So here you can see, well, while those textiles walk outside for about 10 minutes, your clothes temperature increased by about 0.2 degrees C, then to provide this kind of active thermal regulation. So we can also use them for implantable this kind of electricity generation as well. We can integrate this device into the deep tissue because this device is intrinsically waterproof. They're able to convert this ultrasound mechanical wave into electricity. So when the implant depth up to about 5 millimeters, they can also generate a current up to 1 milliamperes. So 1 milliamperes is extremely high. Actually, is a record among all of the other platform technology for implantable electricity generation. And more important, this device is intrinsically waterproof. You don't need to worry about it. So we'll look at those bioelectronic devices, no matter the membrane devices or the magnetoelastic membrane I introduced previously. So because those electrons are always made of solid materials. So the solid material will cause some problem. They have a mechanical mismatch and they have a poor conformity with the human tissue. So what we think about, can we develop liquid bioelectronics? Because liquid materials usually have ultra-low Young's modulus, and they have very good reconfigurability, so they can fill the fine trenches in between on the human tissue for like the human skin. So to give us unprecedented conformity, reconfigurability, and also because with the liquid format, they can also be injected into human body. Then we don't need to do the open heart surgery to implant such devices into the for healthcare purpose. But how to developing liquid bioelectronic devices? So that's gonna be a challenge. So as a material scientist, I still look at the materials innovation. Can I use the material innovation to provide solution here? So when we look at the permanent magnetic materials, so usually the solid magnet, like the frigid magnet we use every day, that's because they're in this kind of a permanent solid magnet, they have formation of the aligned domain with the internal microcrystalline structures. Thus give out permanent magnetism. So when we look at liquid magnetic materials, for example, ferrofluid is one of the famous one. Ferrofluid basically consists of 10 nanometer size magnetic nanoparticles, which is well dispersed in the carrier fluid. This 10 nanometer size magnetic nanoparticles have very strong Brownian motion in the carrier fluid. So those Brownian motion can bring advantage that this particle will not be sedimented down to the bottom of the carrier fluid. But this kind of Brownian motion can also have dark side that can cause magnetization, relaxation. Then those materials doesn't have a permanent magnetism. It's a paramagnetic materials. So if you wanted to give some permanent magnetism or give some magnetism to ferrofluid, you have to use some external magnetic field. So basically in nature, there's no liquid permanent magnetic materials. So let's come to our very exciting discovery recently. We named as a permanent fluid magnet, PFM for short. So how to create this PFM? So we just use bigger size magnetic particle, like 1 micrometer size or 10 micrometer size. So those particles that have minimized Brownian motion in the carrier fluid. So they will be easily sedimented to the bottom of carrier fluid. But before that, we use very strong magnetic field to align those particles. Then they are able to form this kind of this three-dimensional oriented and ramified magnetic network structure in the carrier fluid. So you can see basically those kind of structure support between adjacent magnetic particles could defy the gravity of the magnetic particles and give us a very stable magnetic format. And in the meanwhile, those aligned Chen shape can give us permanent magnetism. So basically, it's the first of a kind of materials which both have a liquid format and also have a permanent magnetism. So this work published on Nature Materials last year and highlighted by Nature Materials and Nature Review Bioengineers. So with this fundamental new materials, we can able to build up some liquid bioelectronics. For example, we can build up ultra-sensitive acoustic sensing devices. So for conventional, actually, acoustic sensor made of solid materials. So basically, you can see they always have fine trench between the tissue of the sensor devices. But with these liquid acoustic sensors, you can see basically those liquid materials could feel fine trenches in between to minimize the acoustic impedance mismatch and give us a much better signal-to-noise ratio. You can say when they use the same acoustic wave to excite the both conventional solid acoustic sensor and those PFM-based liquid acoustic sensor, you can see our device has a much higher signal-to-noise ratio, has a much higher this kind of electric output. So those sensors also have a very good self-filtering capability to filter out the acoustic wave with a frequency less than 30 Hz. This is very good for human voice recognition because human voice spans from 20 Hz to 2000 Hz. So they also have a very good resolution, this kind of frequency resolution as low as about 0.01 Hz. And to showcase the potential societal impact of platform technology or these devices, we're able to build up a voice-instructed wheel-to-child. So when people wear those sensors, talk with them to speak to them for go, stop, left, right, back, we're able to use them to wirelessly control the wheel-to-child. Wheel-to-child actually provide convenience to the disabled person. We can certainly use this device to build up a wearable cardiac monitoring devices. We just put a tiny droplet on the west artery site. This kind of auto vibration is able to deform the PFM droplet. With the result, we can generate useful current in internal circuitry. So you can say on a sweat skin, on a dry skin, so you can say that generate possible profiles continuously. And with validated device with conventional ECG and the PPG device, you can see our device has slightly better signal-to-noise ratio. SNR means signal-to-noise ratio compared with this kind of commercialized, this kind of cardiac monitoring devices. So more excitingly, we can able to build up injectable, retrievable cardiac monitoring devices. So basically, we can use a syringe to inject the device to the heart surface of a liver rat. So basically, during this kind of heart beating, you can see our device generate very regular patterns. This generate electric signal for different wave patterns, different cardiac cycles. So validated device with ECG devices, and we're showing that not only this device able to monitor this kind of pulse wave continuously, but also they're able to have very stability against the motion artifact. You can see if there's a motion artifact, the ECG device will induce very large fluctuation in the output signal, but our device is very stable. And this device could inject up as deep as about 8 centimeters. And this device also has very good this kind of biocompatibility as well. And more importantly, after the monitoring, we can use a syringe to take it out. So then to form this kind of injectable and retrievable cardiac monitoring devices. And when we look at bioelectronic devices, no matter the membrane device I introduced previously or liquid bioelectronic device introduced previously, so basically those devices is soft but not breathable. So then they will have a concern about wiring discomfort. So for example, if you just wrap up food wrap around your hand for about 2 hours, you will feel discomfort. Although the food wrap are very soft membranes because those are soft but not breathable. So for bioelectronic devices, usually people expect to wear those devices or impound it for long term, for example, 7/24. So definitely this wearing discomfort will make you feel reluctant to wear such devices. So, but textiles is an indispensable component in our daily life. They have very good wearing comfort. For example, if you wear clothes for about 7/24, 7 days per week or 24 hours per day, you will not feel discomfort. That's because these are very good breathability. And also, our human beings have a long history with textiles. We can use weaving or knitting technology to create those products at large scales to reduce the cost. And also, textile have some other advantages. You are able to convert them into bioelectronic devices. For example, they have a wide range of materials choice from natural material like cell wool, cotton, to synthetic material like peptide, polymer, polyester. Actually, many of them are biocompatible, biodegradable, even bioabsorbable. But when we look at those materials, chemically, they're very inert. It's very hard to induce chemical reaction. Physically, they are not conductive. But if you wanted to make those materials, those textile materials, into biological devices, probably they have some challenge over there. So luckily, we notice that human body have a lot of biomechanical motions. Like when I give a talk, my mouth movement and breathing, my heart beating. So if we are able to use textile materials to first convert those mechanical pressure into electricity, we have some hope there to developing those materials into biological devices. So 3 years ago, Nature Electronics invited us to write a paper to summarize this kind of how can we use textile for personal healthcare. So if you're interested in this review paper, this concept, to read this review paper, how can we build up some textile bioelectronic devices? So here I just wanted to share the first figure with you. That's actually a timeline platform technology developed for small healthcare textiles. So you can see the magnetoelasticity or magnetoelastic effect, that is actually based on textile bioelectronics. That is a very recent one we invented at UCLA, and we are also pioneering research effort in the world. So I think that's the reason the editor-in-chief invited me to write a review paper. You can see starting from 1990s, people never stopping invent fundamental new platform technology to this actually small healthcare textile community. For example, here the electroluminescence, piezoelectricity, photovoltaics, piezoresistivity. So using all of the platform technology able to help you to construct some textile bioelectronics for personal healthcare. So triple electricity is also another platform technology, basically use a concentration between 2 to 7 materials. It's also invented in 2013. We first introduced the textile, the triple electricity in the textile format, actually for the to build up some textile bioelectronics. So if you wanted to build up textile bioelectronics in the community, there are also another grand challenge, that's soft conductive fibers, because soft conductive fibers actually a building block of textile bioelectronics. But in the conventional approach, people usually have used very high pressure, high temperature approach to create those soft conductive fibers. So to solve the problem, so here we invent a phase separation enabled ambient spinning technology. We're able to continuously create those soft conductive fibers with a diameter about 50 micrometers. You can see 50 micrometers basically is the diameter of human hairs. More importantly, those approaches could be utilized to produce soft conductive fiber at larger scales at ambient temperature and the ambient pressure. So with that, actually, we can provide this kind of a simple, scalable, and cost-effective approach to construct soft conductive fibers, which could utilize as a building block to construct a lot of different type of textile bioelectronics. So here I want to show you with those actually platform technologies and also those kind of soft conductive fabrication or manufacturing technology, then integrate them together, so we're able to build up different type of textile bioelectronics. For example, here is the unmasked sensor network for respiration monitoring. So we just deploy some textile pressure sensors onto the conventional facial mask. So use this facial mask, actually, these 5 sensors corresponding to 5 channels of electric signals. So this sensor is very sensitive to the fluid dynamics, fluid mechanics between your mouth and actually your face mask. So by all of general electric signal, we're able to monitor for them normal breath, deep breath, occasional cough, normal voice, respiration failures. So basically with accuracy up to 100%. In the future, it's wear this facial mask then are able to monitor respiration behavior. So we can also use this textile for possible monitoring as well. So this piece of fabric, but it's very pressure sensitive. They're able to, when you wear this fabric against west outer set, are able to convert west outer vibration into high voltage signal. You can see in one cardiac cycles, the 3 typical points like PSP and PD could be clearly read out. So basically, the general electric signal are analog signals. We need to go through steps of signal process and transmission. Eventually, we can use Bluetooth to show the possible profiles in your cell phone app when you wear such a piece of textile sensors. So in the future, when you just wear this piece of textiles or wear this piece of smart clothes, so when you check out cell phone app, you can check your possible profile continuously. And if you found some abnormalities, you can just do a screenshot and share this information with the doctor over distance and get immediate suggestion of health care. So for those kind of sensors based on energy convention, so these are grand challenges. That is, those sensors not only convert pulse vibration into electricity, they can also convert the body movement in electricity as a motion artifacts. So here we just use some machine learning algorithm to integrate it into this text sensor system. You can see that when you wear this piece of text sensors, even when you play basketball, they're able to actually to read out possible profiles because this machine learning can help to get rid of the motion artifact induced electric signal. With the result, we vet these devices when you wear the device, possibly monitoring while you have some body movement. So you can see that actually after validation with the commercial cardiac monitoring, you can see they can give out actually blood pressure very accurately. So actually motion artifact management is a very important research domain in the field of soft bioelectronics. So if you really wanted to advance those soft bioelectronic research from bench to bedside to advance to clinical trials, I think motion artifact management is a problem you have to address. So here, actually for motion artifact on the human body for bioelectron, not only have biomechanical motion artifact, I give example just now, they also have an impedance instability motion artifact and a biopotential motion artifact. So those motion artifacts, all of them collectively impact the monitoring accuracy of the bioelectronic devices. So in this action literature review published on Nature Review Bioengineering last year, is kind of from Carl, you have very systematic introduction or discussion about the 3 different types of motion artifact, including mechanical motion artifact, biopotential motion artifact, and impedance instability motion artifact. So if you guys are interested in this concept, actually read this review paper. I think they can give you some useful information. So certainly we can also use this kind of actually text bioelectron to provide some therapeutic as well. So here we can use them to build up wearable speech translation devices. So this text gloves is able to convert American Sign Language into electricity for wearable speech translation. You can say when you wear this text glove to express actually the standard way, American Sign Language standard way to express the letters ABC, numbers 1, 2, 3, or short phrase I love you. So those generate electricity from different fingers. We can just use general electricity recognition patterns to do real-time wearable speech translation. So here's a video I wanted to share with you. So basically, after publication, this work I highlight a lot of what in this media coverage, including CNN, ABC, NBC, NPR also give me a personalized this kind of personal interview, and I also put out top 10 science story of 2020, and Arithmetic put out a top 100 papers among the 3.4 million works published in 2020 across 20 subjects. So use text not only for actually monitoring as an assistive physics therapy and wearable speech translation devices, they can also provide energy solutions as well. So those textiles are able to convert biomechanical motion, body heat, biochemicals like the lactate glucose contains in your sweat. This biofuels could also utilize for electricity generation and also solar radiation as well. This is also available on your clothes when you wear clothes, walk on the street. So definitely the solar radiation is also available. So basically we can use textiles to convert those kind of energy on the human body or in the surroundings into electricity. So if you guys are interested in using electricity, use textile for energy harvesting per video review paper is entitled Smart Textile for Electricity Generation. The highlight from Harvard Chemical Review and is set about 1,000 times in the past 5 years. So And also we can, for this kind of energy harvesting textiles, they have a disadvantage, that is the energy in nature is not stable. For them, solar radiation in the morning, in the night is very weak, but at noon is very strong. But for the, if you want to use energy to drive some small electronics, those small electrons always have need very stable power source. So with that, we also wanted to use a regulating capability of wearable energy storage devices. For example, here the solid-state zinc-ion fiber batteries. So the fiber batteries actually is able to store the energy harvesting from the fabric, and then at discharge plateau of the zinc-ion fiber batteries, this kind of are able to provide stable power supply for small electrons. We also show that it's actually fiber batteries are very stable against mechanical bending, and also even you soak the batteries into the artificial sweat, they can also maintain very good specific capability. So we can also take a first step to hybridize this kind of energy harvesting textiles with energy storage textiles. So for example, here we can use the fabric solar cells. So if there's sunshine, they can generate electricity. Those electricity is stored in the fabric batteries. So at a discharge plateau fabric batteries, no matter how strong your solar radiation is or how weak it is, so at discharging plateau of fabric batteries, they can always have very stable power supply for small electrons. With that, we can form this kind of self-charging power unit. With this, we can provide a sustainable and a stable power source for wearable bioelectronics, especially in this kind of textile format with very good varying comfort and flexibility. So let's come to the conclusion of my talk today. So my vision to the talk that in the future, we can use different platform technology, different manufacturing technology to create different bioelectronics, no matter in a membrane format, in a liquid format, or in a text format. So some of them will provide diagnostics, some of them provide therapeutics, some of them provide energy to form this kind of body area bioelectron network to give us 7/24 all-around healthcare. So if you guys are interested in this concept, we clearly picture this concept in this recently published paper on Chemical Review, highlight from cover in 2022. If you get interested in concept, read the review paper as well. Is also well cited in the community as well. So then come to a part of my talk today. I would like to thank my bioelectronics group with a number of postdoc and Ph.D. students, and also my collaborators, contributors, and also the financial support from different funding agencies in the past 6 years when I am with UCLA. So lastly, but not least, actually, this is a picture show the beautiful campus of UCLA. You can see it's quite beautiful and peaceful. And here is LA downtown. It's about 30 minutes driving distance. So that's make the campus very safe and also peaceful and very beautiful. So if you get welcome you to UCLA in the future, thank you very much for your attention, and I'm open to take any question if you have. So any question?
Any questions from the audience?
Yeah,
Professor
don't
Chen,
be shy. Feel free to ask me some questions.
Professor Chen, that's a wonderful seminar you gave with a lot of applications of magnetoelasticity. I was wondering, you see, for a guy like me who wears a pacemaker, will the magnetic field have any adverse effect at all on the pacemaker?
Yeah, that's a very good question. So definitely we're able to attach this devices because especially magnetoelastic patch, usually waterproof and biocompatible. We can attach this patch to the heart surface and convert the heart beating into electricity and to drive the pacemaker. Yeah, we can do that, and actually we are doing that as well. Yeah.
Oh yeah.
Yeah.
Krishna, we have a student question.
Sure, yeah.
Hello, I came here a little bit late, so I don't know if you addressed this earlier in your seminar, but I was wondering if your fabric, does it overheat?
You mean fabric overheat?
Yeah.
Yeah, so certainly that's a very good question. So because for this kind of energy conversion devices, they always generate heat during the operation. So yeah, so this is for energy harvesting devices, we usually wanted to make the electric output very high, so that will generate more heat. But for the sensing device or stimulation devices, sensing device, we just generate very tiny current voltage, usually in the range of several microamperes or several nanoamperes. So with that, because for sensor applications, the heat generation is actually is always near, is almost very minimal. So they will not increase or temperature of the device. So, but for energy harvesting device, certainly we have concern over there. Yeah.
Thank you.
So that depends on your application scenarios. Yeah. Very good question. Yeah.
In the detection of COVID-19, do you have any data on the detection of viruses?
Oh, yeah, that's a very good question as well. So basically, our device mostly focus on the biomechanical part. That's biomechanical information during the breath. For example, if you have COVID, your breath will become very, very quick, but very shallow. So then the general electric signal will usually have a higher frequency and lower amplitude. So we can only check those information during the breath. For the virus, probably is probably we need to use some analytic chemical sensors. So that's actually is not that's a beyond capability of our platform technology. So our platform technology both on can only read out the biomechanical information rather than the biochemical information during the breath. Yeah.
Mm-hmm.
So any other questions?
This is Sushila Kanodia from the California section in Bay
Yeah,
Area.
Sushila, yeah. Let's
Can you hear me?
Yeah, sure, yeah.
Wonderful talk. Excellent work. Is any
Thank
of
you.
the stuff available for public to buy, like for Parkinson disease, the detection of the tremor using the keyboard or the pen or wearing the shirt to understand your heart rate and all that stuff? How, is it already available or is it going to be soon available?
For sure, it's going to soon be available because I just joined UCLA in July 2019. So we filed all the patents you mentioned just now, but we are starting up companies, but it just takes time to bring those products to the market. Yeah.
Thank you.
Thank you for the question. Yeah, thank you. Yeah.
And is there any way that for a blind person, this kind of device can help in reading or listening or something like that?
Listening,
No,
reading.
reading, especially for a blind person.
Okay, reading. So that so probably we can but I didn't do that. But probably we can provide solution over there. Yeah, for the blind people reading, they have to reading by touch, right? Yeah. So yeah, probably we can do that. Yeah.
Right.
Yeah.
Are there any other questions?
So I'll ask just how Dr. Chen, how is your funding? Do you feel like your funding's stable for the in the current kind of chaotic situation?
Linda, I beg your pardon?
The research funding, I know some of it you said was NIH or NSF. Is your grant funding stable?
Funding.
So I'm luckily it's stable. Yeah. So yeah, I really appreciate the funding support from NSF and NIH. over the past years. Yeah.
Yeah. It looks to be one of the best sensors are wonderful devices for various kinds of disabilities. And I'm pretty sure that our American Chemical Society, the Committee on Chemistry with Disabilities, they will be extremely interested in this kind of research and work. And I'm going to pass on some of the information that you have put in there to the Committee on Disabilities, and I'm pretty sure they are going to be fascinated and very excited about helping disabled people with this kind of research and this kind of, say, devices. So it looks to be very promising for disabled people, especially. Would you comment on that?
Yeah. So for disabled people, definitely, yeah. So depend on uh, how is the disability. So basically, for example, so far for the people who has dysfunctional vocal folds, people cannot move. So people cannot people cannot speak. So
Mhm.
we already provide solution in to those group of peoples are indicated in the previous presentations. So definitely we will expand our applications as widely as possible to help the disabled group are the better in a better way, and we are still explore those directions and to see can we provide more convenience to a different type or to a wider range of disabled group people and to help them. So yeah, we are still doing that. Yeah.
Yeah,
Yeah.
especially the sign language and the automated movement of wheelchairs. I
Yeah.
think those
Yeah.
those two are extremely attractive and very, very, very important for disabled people as I look at it. Uh, well, anyway, if there are no more questions, it is my pleasant duty to thank Professor Jun Chen for an
Thank you.
extremely scintillating seminar and very informative and very, very practical, not only from health and energy points of view, but also from various other angles like even climate change mitigation, things like that. So on behalf of the SCALACS and the Georgia local section and the Senior Chemist Committee of the National ACS, my sincere thanks to Professor Chan for accepting our invitation and making a scintillating presentation. Thank you, Professor Chan.
Thank you very much for your for your time and attention to my talk. And lastly but not least, my group have multiple opening for PhD student and postdocs. If you guys interested in this research, please contact me. You can easily find my information by use Google Chen UCLA, and then you can easily find my email address. And thank you very much again for this great opportunity to share my progress with you guys. Yeah. Thank you. Yeah.
Thank you. Bye then. And thanks everybody for attending.